Section 6.2, Algebra 2, applying properties of rational exponents. This is a little bit of a challenging section. It is definitely going to test your knowledge of our properties of exponents, and we're going to take a look at how exponents and radicals are related. And it's a good thinker section. So you're definitely going to have to be paying attention to what you're working with here. These properties of rational exponents that we see here, we've seen these properties before in the previous chapter. We've got some product properties, some quotient properties, some power of power properties going on, and these are the ones we're going to be using throughout this section and then the rest of the chapter here. A lot of times, though, in this section, we do see stuff maybe written in this form, for example, and we're taking it out of that form and putting it back into this form, or more commonly for maybe products, maybe we see things written like that, and we have to transfer it back to something. So just make sure that we're able to go both directions with these problems here. Understand how we can go from one way to the next. All right. So with a pretty decent grasp on properties, let's go ahead and tackle some of these. We're going to take a look at some more challenging problems as well after we get through with the lesson here. So using our properties to simplify, we have here a situation with problem A where I've got the bases are 12. And I am, this isn't an X, it's supposed to be multiplication symbol, so that's what's going on here. Multiplication, multiplication. I could have written it with parentheses, I guess. So 12 to the 1/8 times 12 to the 5/6. And in this case, with my bases being the same, that means we can leave our base and we simply add our powers. Now, because I have powers that have different denominators, I'm going to have to create common denominators. And we know for an 8 and a 6 that I've got a 24 as my common denominator. And let's see, 8, to make the numerator different, we would do the same thing to the numerator as we did to the denominator. So how I make an 8 become a 24, I multiply by 3. I do the same thing with the 1. And then how do I make the 6 become a 24? We multiply by 4. Do the same thing with our 5. And we finally get 12 to the 23 over 24th power. All right. And we can go ahead and leave that alone. As usual, as I'm working through the examples, if you want to try some before I get to the example, pause the video. Here in this next problem, we've got a situation where I have unlike bases, and I have this power on the outside, and the power of power says I raise to the power of 3 everything on the inside of this parenthesis. So this becomes 5 to the 1/3 to the 3rd power times 7 to the 1/4 to the 3rd power. And then now I'm just raising 1/3 to the 3rd and 1/4 to the 3rd. And that's going to give me 5 to the 3/3, or 5 to the 1st power, times 7 to the 3/4 power. And it might be rather tempting to multiply that 5 and that 7 together, but because they are different bases, I am unable to do that. So I'm just going to write, my answer is 5 times 7 to the 3/4 power. All right, 10 divided by 10 to the 2/5. They are like bases, so I'm able to apply my properties. Now, when I don't see an exponent on there, it's a 1. So I have 1, and then I'm subtracting 2/5 from this. Well, common denominators would mean that 1 is the same as 5/5, which makes this 10 to the 3/5 power. about here? What's unique about this problem is, although I do not have like bases, I do have like exponents. So we're going to see, in one of the cases I was pointing out earlier with our properties, we're so used to seeing maybe the left-hand side of the property and converting it to the right-hand side, but maybe not seeing it the other way. That's the case here in this situation. So we're going to raise everything to the power of 5 here, and we get 56 to the 1/4 times 5 power, 7 to the 1/4 5 power, giving me 56 to the 5/4 power, divided by 7 to the 5/4 power. Now what's unique here is that, again, we still have a situation where I've got the same exponents. And I could have worked the problem out by looking at the inside of the parentheses first and done this, where I rewrite 56 over 1/7 all to the 1/4 power and then raise to the 5. I could have done it that way. That would have given me 8 to the 1/4 power, all raised to the 5th, and 8 to the 5/4. I'm going to get the same thing over here, because what happens here is I see that 56 divided by 7, they both have the same exponent, so I'm able to write them as a quotient to the power of 5/4, and this would become 8 to the 5/4 power. And then we're going to actually take this a little further. When my exponent is an improper fraction, we're going to break that improper fraction down into its whole part and then its fractional component. So what do we mean by that? Well, 5/4 is the same thing as 1/4 times 4/4. So if I were to break 5/4 up, and again, here we are seeing the reverse property. 8 to the 1/4 times 8 to the 4/4 gives me 5/4. And the reason we're doing this is because that's my whole part, which just gives me 8 times 8 to the 1/4. And that's really as far as we're going to go there. If it were written as a radical, which I think we're going to get to some of those later, we'll see how we can deal with it in the radical form. So you are able to always go back and forth. If you're comfortable with working in exponential form, then switch to radical form, you can do that. Or going the other way, radical form, switch to exponential. Right, again, we have a situation where I have unlike bases and unlike powers here. So the only thing we can do for E is raise everything. So 4 to the 2/3 cubed. And then I've got 5 to the 3/4 cubed. And that becomes 4 to the 2nd power, because the 3 and the 3 are going to cancel. And then 5 to the 9/4 power. And 4 squared is 16 times 5 to the 9/4 power. And then once again, I've got that improper fraction, so I can pull out a whole component. So 16 times 5 to the 5/5 and 5 to the 4. Oops, denominator 4, not 5. So 5 to the 4/4 and 5 to the 5/4. Or recognize that instead I've got 8/4, so I can pull out actually 2 whole parts. And then I get a 16 times a 5 squared times 5 to the 1/4. And that 5 squared becomes our 25. So 16 times 25 times 5 and 16 and 25 becomes 400, and we get that. 400 times 5 to the 1/4 power. So whenever we have these improper fractions, break them up into whole parts and fractional. All right, very good. Let's talk about the radical world. Radical properties mirror their exponential properties. So here we see a situation where I've got a product, and I'm able to take that product and put it into its factored form. And going back, we have that same thing going on here in example 3. We had a product of A, B that we break into the factors of A and B. All right, so we are able to use similar properties with radicals as we were with our exponents. All right, so let's do some simplifying here with these. Cube root of 125. It is great if you happen to know your perfect squares, cubes, fourths, fifths, sixths, for numbers, say 1 through 9, for the first 3, 4 powers. If that's the case, you will recognize that a 125 is actually a perfect cube. It's actually the same thing as saying 5 cubed. And then we have a property of power and exponents being the same. I mean, root and exponents being the same. And when that happens, you just get your radicand. So what that means is this just becomes a 5. Now, had you not recognized that 125 is a perfect cube, and you went ahead and you started breaking it down, you said, well, I know that 25 goes into 125 5 times, and then 25 goes into itself, or breaks down into 5 and 5. Then you have your prime factors. And here's the cool thing about breaking it into prime factors is that in this case I have cube roots. And anytime I have 3, because it's a cube root, 3 of the same prime factor, cube root 5, cube root 5, cube root 5, then all that comes out of this is just the radicand. So the power number on a radical, this tells me the number of identical roots I would need for there to just be a radicand that comes out of the problem. And that's kind of going on with that. These two match, then just A results. So let's keep that in mind as we work through these problems here. All right, here we have 2 radicals, and I could separate fifth root of 96 and try and break 96 down into its factors, and hopefully one of those factors is a fifth or a perfect fifth. But I ideally would do the second option, and that is recognize that I could rewrite this as a single fifth root of 96 over 3. And this becomes much easier for me to work with because now I can see that 3 goes into 96 32 times. And hopefully I recognize that 32 is a perfect fifth, which means I just get a 2 there. All right, let's keep going. Good practice on reducing things. So here, I could, let's see, if we broke it into a single radical, we have 245 over 5. And that goes in let's see, goes in 49 times. So this is the same thing as the square root of 49. And that's nice because the square root of 49 is a 7. And they started as principal roots, so they're starting as square roots, so we're just going to write 7 and 7 plus minus 7. What about writing the expressions in simplest form? Kind of pretty much the same thing we were doing here above, just more practice of the simplifying part. 104 is not a perfect cube, so what I'm going to have to do here is I'm going to break it up into two factors of 104. And if I'm looking at 104, I know I can get, let's see, an 8 and a 13, I think, go into this. Now, why do I choose 8 and 13 instead of doing 2 and 52, and then break 52 down into 2 and 56, and then 56 breaks down to 2 and 28, and then that breaks down to 2 and 14, and that breaks down into 2 and 7. The reason I chose 8 and 13 is because I have a cube root, which means I would love to have a perfect cube underneath that radical, and I do. So this perfect cube of 8, which just becomes 2, and then I have a cube root of 13 that can't really do anything, so I'm done right there. 13 is prime, I can't break it down. So if I can identify perfect factors of our numbers that happen to be perfect, whatever the nth root is, then that's a quicker way of simplifying these problems. All right, 4th root of 10, 4th root of 27. Another one where I might look at this and say, let's do 10 over 27. And let's see, there are no factors of 10 that also go into a 27. So I'm kind of dead in the water right there. Can't do much beyond that. There is another thing, though, we can look at. And that has to do with always being aware of what radicand values are. And if your radicands can be written as an exponential number, there are times when that will be very helpful in the simplification process for us. In this case, we're going to take that 27, and we know it's a perfect cube, so we're going to rewrite this as, and I'm going to go back to looking at it in separate radical form here. Cube, 4th root of 3 cubed. Okay, so what do we do with this? I would love to make that thing underneath here. I'd love to make this a 3 to the 4th power, so that when I take the 4th root of it, I end up with just a 3. And this is just rationalizing. We're rationalizing our denominator to get rid of that radical down there. And how you do it when it's an exponential form is I have a 3 to the 3rd currently, and I want to end up with a 3 to the 4th underneath this radical. So, just using my properties of exponents, 3 to the 1st power, if I were to multiply that by 3 to the 3rd power, I would get 3 to the 4th. And that's what's going to happen down here in the denominator. I'm going to raise to the 4th power 3 to the 1st. I'm going to do this on the top and the bottom. And again, the reason I'm doing this is I'm getting rid of that radical in the denominator. Where in the previous problem, when we had the radical in the denominator, we were able to get the radicand 96 over 3 just came reduced into a 32. It was nice. And the same thing happened here. It just became 49. That's not the case in this problem. So we're going to go ahead and we're going to rationalize. Now I get a 4th root of a 30 and a 4th root of a 3 to the 4th power, which means just a 3. And at that point, even though 30 perfect fourths, and so I'm unable to go any further with that problem. Okay, got another one down here. Take a look at this. We've got another situation where once I break it into 2 cube roots, I have a problem with the denominator being a radical. So, again, talking about cube root. I've got a cube root of a 9 right now. What would I love to multiply a 9 by so that I ended up with something inside that was a perfect cube? But there's going to be 2 ways to look at this. Some of you might recognize, oh, that needs to be a 3. Another way to look at it is, all right, well, if this is 3 squared, kind of modeling what we just did above, cube root of 3 times cube root of 3 squared just becomes 3 on the bottom. So that's what I'm going to end up having to do, is a cube root of a 3 on the top and the bottom. So I get a cube root of 27 on the denominator, which just becomes 3. Multiplying again. So I have a cube root of a 15 over a cube root of a 27, which is just 3. And now it's real tempting to take that 3 and divide 15 by 3. I cannot do that because it's not a 15 in the numerator. It is a cube root of 15, so I cannot divide it. And there's my final answer for that. So beware of radicals in the denominator. We must rationalize them. And prior to doing this section, we always had radicals that were square roots. And so what we always did was we just multiplied by the same thing that we see down in the denominator. We cannot do that anymore when it's not a square root. I need to make perfect, in this case for problem C, I had to make perfect cubes. We were making perfect squares down here because 2 times 2 was a 4, and when I took the square root of a 4, I just got a 2. So we were doing this concept of making perfect nth powers, but now we're going to have to be dealing with powers other than 2. So we make perfect fourths or perfect sixths, the perfect cubes in this case. The process is still the same though. All right, what about adding and subtracting? So we've been dealing with the multiplication and division properties. What happens when you have radicals that you add and subtract? Well, what you want to think about with this stuff is combining like terms. That's really what we're doing here. Where our like terms are just radical form. So we're looking for the same radical. It's got to be the same root and the same radicand. So they all have to look the same. And that's what's going on here. We've got 2 of the same looking radicals. We've got a 5th root of 12 and a 5th root of 12. I start with 7 of them. I remove 1. So 7 minus 1 gives me 6 5th root of 12s. And at that point, it's as far as we can go with that. Let's give ourselves some space here. All right. Let's take a look at these other examples then. Looking for the same radicals, or in this case, same exponents. Exponentials, which means same base and power. So we can do same exponentials, we can do same roots. They are both like terms. So here I see I have a 9 to the 2/3 and another 9 to the 2/3. I have 8 more of them, which means I have 12 times 9 to the 2/3 power. Okay. Cube roots again, 81 and 24. Now they are not the same. So what we need to do when we don't end up with something that begins with the same look is that we see if we can simplify them by maybe factoring them to make them end up with the same radical. And that's what we're going to do here on C. So looking at an 81, I know that a cube root of a 27 and a cube root of a 3 and 27 make an 81. Why did I do 27? Because it's a perfect cube. So that means this just becomes 3 cube root of 3's. And hopefully, when I break down this next number, 24, I'll end up with another cube root of 3. And look what happens. So we have another perfect cube. I have cube root of 3, cube root of 3. And we end up with just 1 cube root of 3, or just cube root of 3. After I subtract 2 of them from 3 of them. How about 48? Well, cube root of 4th root of 3 is already prime. So can I take a 48 and somehow get a cube or a 3 factor? And I can. 3 goes into 48 16 times, and 16, 4th root of that, that's a perfect 4th. So now I have 2 times the 4th root of 3 minus a 4th root of 3, and again, giving me just 1 4th root of 3. So looking for those like terms when you're adding and subtracting. Variable expressions, the properties of rational exponents and radicals can also be applied to expressions involving variables. Because a variable can be positive, negative, or 0, sometimes absolute value is needed when simplifying a variable expression. So when our n values are odd, when our roots and our n values are odd, we just have a situation where the matching powers just result in the radicand, whatever that value is. When it's an even thing, as is the example over here on the right, what if our base is a positive 3? The even powers, the base just comes out. What if our base is a negative 3? In this case, we think absolute value. And why we're thinking absolute value? Because if you look at this example right here, and we had a negative 3, and we raised that negative 3 to the 4th power, we get an 81. And the 4th root of 81 would be a positive 4th root of 81 would be just a 3. So we're going to think about absolute values when these n values are going to be even here. So let's carry that concept into these next examples here. So we do have a 4th root here, so this is an even. And in this problem here, we're going to break it up into parts. So we're going to always think about simplifying by breaking into pieces. If I start with a very large radicand that's made up of variables and numbers. So here we are breaking it up into a 4th root of 625 and a 4th root of z to the 12th. Just so happens that 625 is a perfect 4th, and it means 5 to the 4th power. Now, variables with roots and power numbers, there's a cool little trick we can do for these things. Z to the 12th. If I think about trying to somehow match my power and my root and my power, we know that if I am able to do that, then the radicand, the base value, is just what comes out as my solution. So I want you to think about z to the 12th and how we can rewrite z to the 12th. having an exponent of 4. So am I able to write it so that I get a 4 out here? C to the something would give me 12. Well, if that started as a C cubed to the 4th power, that's giving me C to the 12th. So if we looked at this as the 4th root of C cubed to the 4th power, now I have my root and my power number matching. So all that comes out of this would be a C cubed. And my answer to this would just simply be 5C cubed. Now another way to look at it is ask yourself the question, how many 4s go into a 12? And the answer is 3. That is where this is coming from. So when that root number divides nicely into that power number, the solution we get there just becomes the exponent of my simplified radical. So how many groups of 4 go into 12? 3 groups of C, or C cubed, goes into a 12. We'll look at what happens when that number on the root radical side, or in the exponent side, is an odd, for example. 4 into 13 doesn't work, so what do you do then? We'll come up with some examples for that in just a second. But this is how you're thinking about these problems. Breaking them into power pieces. All right. So let's work through these next group of numbers here, or next group of examples. For the B, nothing to do on the inside in terms of simplifying, so that means we're going to raise everything to the 5th. So 32 to the 5th, m 5th to the 5th, n to the 30th to the 5th, and 32 to the 5th is the same thing as the 5th root of 32, and that's just a 2. M to the 5th to the 1/5 just becomes 5/5, or 1. So that just becomes an m. And then this is n to the 30 over 5, which is just n to the 6. So this whole thing becomes 2m n to the 6. So you're going to just break it up into pieces like this. 6th root of r to the 6th over s to the 18th. So because r and s are different bases, I can't do anything with these powers. So what we can do then is just work with individually our radicals on the top and the bottom. So we separate it into 2 6th roots. Now we work them individually. And here we have powers matching, power and roots matching. So I just get an r up there. And then here we go, asking the question, how many groups of 6 go into an 18? 3 groups of 6. Again, how did I get that? S to the 3rd to the 6th power is the same thing as s to the 18th. Matching the root to the power, giving me just the base as my solution. All right, what do we do here? 56 and 7. Not being raised to any power. They're going to just reduce, become an 8. Then we've got some a's and a to the 5/6. So I've got an a over an a to the 5/6. And then looks like we just got a b that's by itself, b to the 3/4. And we have this c value. It's negative. We want to make it positive, so we're going to kick it up here. And we get c cubed. All right, let's simplify all of this stuff. So we'll get our 8. And then our a, well, this is the same thing as a 6/6 here. Which means I'm going to subtract the exponent. 6/6 minus 5/6. And then the b doesn't do anything. The c doesn't do 1/6, b to the 3/4, c cubed, and can't do anything else beyond that, so at that point we are completely simplified. All right, so just some more expressions to simplify here. Another one where we can chunk this thing into pieces. So the cube root of 6, the cube root of x to the 4th, the cube root of y to the 9th, the cube root of z to the 14th. All right, let's go piece by piece. Cube root of 6 is prime. Can't do anything. We're going to have to leave that one alone. Cube root of x to the 4th. So here we have a situation where our root number doesn't go nicely into our power number. However, when your root number is smaller than your power number, you know that you're going to have at least some value of your variable that's going to come out in front of your radical. So here we go, looking at that x to the 4th and how you could write it differently so that you can see what comes out. X to the 4th is the same thing as x cubed times x to the 1st. So we have a group of 3, one group of 3 that comes out, and I have an x that's going to have to still hang out and reside underneath my radical. So far I've got a cube root of 6, and then an x that's come out, and then there's still a cube root of x that's on the inside. All right, what about the y 9th cube root of that thing? So here the 3 goes into 9 nicely 3 times. That means this is just a y cubed. And then here's the situation again. 3 does not go into 14. It goes in 4 times with 2 left over. So z to the 14th could be written as z to the 4th cubed times z squared. 12 and 3, or 4 and 3 is 12. 12 plus 2 is the 14. So here we see that if I took a cube root of a z4th to the 3rd power, just a z4 comes out of that. And so that's what happens here. I get a z to the 4th that's out in front, and then on the inside I still have a z squared. So z to the 4th, and then a cube root of a z squared. So don't forget to include your roots. Don't just start writing radicals and making them become square roots all of a sudden, because they're not. This is a cube root. All right, now what you do is everything that is a radical stays as a radical, and the parts that are non-radical just move out in front. So this whole thing becomes x, y cubed, z to the 4th, that's all the stuff that's not in the radical. And then I have a 6xz squared that is still on the inside. That's my radical. Next one. So 7th root of p to the 8th. 7th root of q to the 5th. All right, on the top, we know that at least a p comes out, and I have a p that's left over. Now, on the bottom, though, when your root number is bigger than your power number, this is where you're going to have to think about, okay, we got to rationalize this thing. So I have a 7th root of q to the 5th, and now I got to make that q to the 5th become a q to the 7th. That's what I want it to be. Something to the 7th power, which means q to the 5 times q squared makes q to the 7th. So if I multiply both top and bottom by q squared, 7th root of q squared, I get p times the 7th root of pq over the 7th root of q to the 7th, which is just q. And our last one. Break it into parts. Fourth root of a squared. Fourth root of b to the sixth. Okay, so in the numerator we have a unique situation. We haven't seen this before. Fourth root of a squared. So unlike the situation where the root number is smaller than the power number, we have it switched. Now the root number is bigger. However, we do notice that the power number goes into the root number 2 times. So you could just simply do this. Both of them are reduced by 2, and now I get a square root of an a. Now on the bottom here, and I'll show you another way to look at that in just a second. On the bottom, you have, okay, a b to the sixth, and a b to the sixth can be created from a b to the fourth times b squared. So that there's a b that's going to come out, one b that comes out, and then I still have the fourth root of b squared on the bottom. And then look, we got that same situation where the root number and the power go into each other, so divide them both by 2. And now you get a square root of a times over b times the square root of b. And I got to rationalize now. Square root of b, we want that to go away, so we multiply top and bottom by square root of b. Square root of ab over b times b, or square root of ab over b squared. All right, now let's go back and look at this. How are we able to take these roots and powers and reduce them the way we were? Let's take a look at the fourth root of a squared. And here's where some of you might prefer to write things in exponential form to see this. So if I change this into exponential form, this becomes a to the 2/4 power. Well, 2/4 is reducible to 1/2. And now we're in a situation where there's my root, there's my power, it just becomes the square root of a. So that's what's happening here. When I've got a root number that is divisible by a power number, I can just simply simplify it like that. So you're going to have to be on the lookout for all these cool little tricks because there are a bunch of them. Radicals in the bottom got to go away. Fractional exponents actually in the denominator, we need to make them go away too. All right, we're almost done here. Then we're going to take a look at some extra examples. So back to our simplifying. I've got situations with radicals, just like with exponentials. We've already talked about they're the same. Have like terms. So 18 minus 11 cube u's gives me 7 cube root of u for this example here. And once again, do I see the same thing? A to the fourth, b to the 2/3, b to the 2/3. So it's like, what if I chunked those and put them as their own piece, and then looked at 15 of them plus 8 of them, giving me 25 or 23, a to the fourth, b to the 2/3. Yeah, that's as far as we can go there. Right. And then here, both of them are fourth roots. However, they're not the same. So prime, I'd love to take this 80 and break it into some stuff I can work with. And I'm going to try and do the same thing with my exponent. So 5 is prime, 80 becomes square root of 16 square root of 5, which is just 4 square root of 5. All right. So I have, so far now, with that, I've got a 10 times the fourth root of 5x to the 7 minus a 4x to the fourth root of 5x cubed. Well, we still don't have what we need. My powers are different. So in this case, I see if I can somehow fix this. I do have the same cube roots, but they just don't have the same radicand values. But what happens here is, in this situation where I have the fourth root of an x to the seventh, let's just take a look at it kind of separately. We know that that means I have one group of 4 that comes out, and then I have 3 left over. And then look at it. We end up with the same thing on the inside. So that's what we're going to do here. We're going to take the 10, we're going to pull out an x. We still have a fourth root of a 5x cubed minus a 4x to the fourth root of a 5x cubed, like terms here, leaving me with my 6x fourth root of 5x cubed. And we're going to take a look at some extra problems here. So we're going to skip, look at maybe some more difficult problems that might illustrate some of the tools you're going to have to definitely be working with. One of the problems we're going to look at is the problem of 64 to the 5/9 power times a 64 to the 2/9 power divided by a 4 to the 3/4 power. Okay. And we'll look at one more after this. So when you first look at this problem, some of you might look to recognize the bases on the top are the same, and therefore I could write them as a 64 and then add the powers together. Some of you might also recognize, and this is something you're going to try and get in the habit of, is recognizing if you can make all of the bases become the same thing. So a base of 4. 64 is actually a base of 4 number. What do I mean by that? It's an exponential of 4 to the 3rd. So if we can make all of these become base 4 numbers, that's going to help me when it comes to the quotient part. Up in the numerator, I'll have some addition going on, and then I'll have some subtraction after I've worked with the numerator. So we're going to change this. We're going to make 64 become 4 cubed to the 5/9 times 4 cubed to the 2/9. And then all of this is now over the same number, 4 to the 3/4. All right. Well, we get 4 to the 5/3, because 3 goes into 9 3 times, 3 goes into 9 3 times 4 to the 2/3, all over 4 to the 3/4. Let's come down here. Up in the numerator, since the bases are the same, we can add their powers, 5/3 and 2/3. And we get 4 to the 7/3, 4 to the 3/4. Now we can subtract. So 4 to the 7/3 minus 3/4 becomes 4 to the common denominator, 28/12 minus 9/12 becomes 4 to the 19/12. And then here is where it gets interesting. So we have 4 to the 19/12. Now another way to look at it, radically, is the 12th root of 4 these things exponentially or radically here. All right, based on what we were working with before, we say that how many groups of 12 go into a 19? Well, there's one group that goes in, which means a 4 comes out. And then I still have on the inside a situation where I have the 12th root of 4 to the 7th. Because again, we took 4 to the 19th and we broke it into 4 to the 12th times 4 to the 7th. And that meant that part of it just gave me the 4 that's on the outside of this thing. All right, and we end up with this. Now here is the unique situation that we're going to always try and make ourselves aware of. Whenever your base number on the inside of a radical happens to be exponential, meaning I can write it as an exponential number, you're going to want to do that. We're going to want to change this to an exponential number because by doing that, we're going to see that some other constants are going to come out of this equation, or out of this radical situation. So 4 is the same as 2 squared. So now we're going to write it as 2 squared to the 7th power. And this problem becomes 4 times the 12th root of 2 squared to the 7th, or 4 times the 12th root of 2 to the 14th power. All right. From there, so we're here, 4 times the 12th root of 2 to the 14th power. Once again, I have a situation where my root number is smaller than my power, so we ask the question, how many 2's can we pull out? One group of 2, because we have 12 goes into 14 once with 2 left over. So now I have a 4 and a 2 that is now out in front. I have a 12th root of 2 squared. So really I got an 8 times 12th root of 2 squared. Look what happens with the root and the power now. That becomes 2 into 12 is 6 times. And I get 8 times the 6th root of 2. Excuse me. And that's as far as we can go for that one. So be looking, once you've taken yourself to a point where we were here, where we thought we were just as far as we can go, we look at those base numbers inside of my radical and see if I can rewrite them as an exponential, and it sends me down a whole other path. Now another example that we could look at is one that involves rationalizing, but not with radicals, but with exponents instead. So 11 to the 2/5 over 11 to the 4/5. These are just some example problems that were in the book. Well, looks pretty harmless. 11 to the 2/5 minus 4/5. That becomes 11 to the negative 2/5. And if we write it as a positive exponent, it becomes 1 over 11 to the 2/5. Now, 11 to the 2/5, remember, is actually the 5th root of 11 squared. And we don't want radicals down there. So I'm going to show you how you can work with exponentials and rationalize them. Instead of changing it to a radical, you can work directly from the exponential. All right, we know if I want to make this thing have no fractional exponent in the bottom, that would mean I would love to figure out what do I multiply 2/5 by so that this thing just becomes a 1. Or not multiply, but what do I add to 2/5? What do I add to 2/5 so that this thing just becomes 1? Well, we know that if we added 3/5 to 2/5, I create 5/5, which is this 1 value. And that's the power I want to see in the denominator. So now we're going to rationalize with exponents I'm going to rationalize with an 11 to the 3/5 power on the top and the bottom. That gives me an 11 to the 3/5 power over an 11 to the 5/5, which is 1. And then if I wanted to write that as radical, I have the 5th root of 11 cubed, and that's the same thing as the 5th root of 1331 over 11. And we're going to write all of our problems in radical form. We're not going to leave them in exponential form. So there are a couple more difficult problems from the text.